Hi guys, welcome to Amateur Chemistry. So recently I've been looking through some old things left over after my great-grandfather, and it's honestly quite cool to experience even a tiny bit of what the world was like in the early 90s. Now, amongst some old aluminum kitchenware and a good bit of fishing equipment, I found this random plastic bag which at first glance looked quite boring. Upon looking inside, however, I stumbled upon by far the coolest thing, or more precisely things, in this whole antique collection. You see, the bag turned out to house a few dozen of these beautifully preserved photographic films, each containing many photos taken when photography was just beginning to take off. I am really glad nobody threw these films out, since they are a wonderful piece of family history and what's perhaps as important on this channel, chemical history. Back in the day, taking and developing photos involved a myriad of interesting chemical processes and compounds, a good example of which is the film itself, often made of nitrocellulose, which is the same stuff the military now uses for smokeless gunpowder. Turning memories into gunpowder was actually the first project idea I had for these films, but after thinking it through, I couldn't live with myself if I wasted my grandpa's work. Instead, after some intense reasoning, I realized that I could use my films for their intended purpose and turn them into real photos. To do these films justice, I decided that I will make the chemicals required to develop photos from them myself, and this alone really tickled that amateur chemistry soul of mine. One problem, however, is that the chemicals used for this kind of thing are often incredibly exotic and toxic, which didn't really resonate with me wanting to make this project as family friendly as possible. Because I didn't want to give up so easily, I went on a research rampage, and after going to many weird places on the internet, I found the holy grail of amateur photography. It's something called cyanotyping, and not only is it almost completely non-toxic, but it's also weirdly straightforward and versatile, and what's even better, I can make the required chemicals from literal rust. Now, if you know me, you can probably guess that when I realized this, I was just ecstatic and really eager to bring back old memories using my amateur chemistry skills in this gem of a project. First, however, I think it's best to dive a little deeper into what cyanotyping really is, since I haven't stumbled upon such a diverse topic in a long time. Okay, so similarly to photographic films, cyanotyping turns out to be very rich history-wise, dating back to as far as 1842 and being one of the earliest methods of photographing things. The whole idea behind cyanotyping is that you make this light-sensitive iron solution, spread it on something absorbent like paper, and after it dries, you can place something you want to quote-unquote photograph on the coated surface. If you then expose everything to sunlight for a few minutes and use some water as a developing bath, you get an image with a white outline of the thing you made the cyanotype of on a blue background. Now, cyanotyping sounds pretty simple when put like that, and unlike most other projects on my channel, it honestly kind of is. In theory, it should work really well with my film, which already has the right tonation and definition of the pictures, or more professionally speaking, negatives, made specifically for this kind of developing process. This alone means a lot, but the main reason why I chose cyanotyping is because of the chemicals involved in making the light-sensitive solution. Normally, processes like this use some weird silver salts or organic compounds which are often a hell to work with. Cyanotyping, however, is an exception since it uses just two quite basic chemicals, both of which contain iron, which is like everywhere and forms the basis of rust. The chemistry of cyanotypes is really unique since iron compounds generally aren't photosensitive at all, and here they not only react with light but also combine to form a very cool pigment called Prussian blue, which is solely responsible for the vivid blue color of a cyanotype. Now, it is composed of two parts, both of which have to be present in the iron solution for cyanotyping to work, the bulkier of which contains one iron atom bound to 6 cyanide ligands. It looks quite spicy on paper, knowing just how nasty cyanide is. However, this so-called ferricyanide ion is actually relatively non-toxic, and sometimes it's even used to treat heavy metal poisoning. If you think about it, it's a really weird compound, and I won't be making this part of the cyanotyping solution myself since that would require the bad cyanide, and since I like my life a little too much to potentially expose myself to it, I just bought some potassium ferricyanide to use for the project. With the ferricyanide sorted out, I now have to look at the other part of Prussian blue, which is made of those lone iron atoms, and since they don't look like they want to kill me, they are the part I decided to make. Now, there are various compounds of iron that can be the source of these atoms, however, only a few are photosensitive enough to be used for cyanotyping. The most popular and least toxic one is this bulky boy called ferric ammonium citrate, which checks all the boxes for being good at cyanotyping and seems to be made from relatively accessible materials. As I already said, I figured I can get the iron part of it from some rust, which despite adding a few steps to the overall synthesis should make this project even more accessible, and to start making some mentally unstable iron, I first had to find some rust. This was easier said than done, however, since after searching around my lab, the only meaningful rust source I found was my lab stand, which despite looking like it wants to die, will still serve me for the foreseeable future, and I didn't want to strip off the few grams of rust protecting its surface. It was really quite funny how of all chemicals I couldn't find rust. Fortunately, after some more lurking around my lab, I found the next best thing, which is steel wool. I had this random piece of it just laying around, and since it's made of the cheapest type of steel, consisting just of some iron and carbon, it's the perfect thing to turn into rust. This would fix my rust deficiency problem and allow me to carry on with the project as I intended, and to start scientifically rusting some steel, I got this beefy beaker and weighed all the wool in it. I turned out to have 24.8 grams of it, which was luckily pretty much exactly enough for the scale I wanted to work on, and to turn these fine iron hairs into rust there are a few methods. Most of them are however way too slow, and even though I purposely started this project months ago to get my rust in a reasonable time frame and at the same time not worry about maintaining anything, I settled on what I call the seawater simulation technique. It involves just covering the wool in a decent amount of salty water and setting up a small air pump to keep everything aerated. Oh yeah. This setup might seem quite puny, but after only half an hour there was already a bunch of nice brown rust forming on the surface of the wool. Now, in terms of what's going on here chemistry-wise, oxygen from the air attacks the iron metal in the steel, turning it mainly into something called iron-free oxide. This process is greatly sped up by the presence of water and sodium chloride, commonly known as table salt. These additives also influence the final composition of the rust, which rather than consisting of pure iron-free oxide, consists of a great deal of iron-free hydroxide and carbonate. They all fortunately behave similar chemically, so from now on I will represent my rust just as iron-free oxide. Now you might ask what's the free in iron-free oxide, and it turns out that iron can actually come in a few different flavors. The most prevalent are iron-free and iron-2, and iron-free is what I need to make ferric ammonium citrate. This conveniently explains why I'm so hell-bent on using rust, since pretty much all the iron compounds in it already have the right flavor. If I were to dissolve the steel wool in, for example, acid, I would end up with iron-2, which I would then have to convert to iron-free using even more chemicals, which, while being considerably faster than rusting it, would make this project less amateur chemistry than it now is. Since to a chemist, time is only a suggestion, I figured that letting my iron rust over a few months is well worth it, and with a whole squad of chemicals beating it up, it quite quickly succumbs and turns into this brown, flaky rust suspension. Now, I originally wanted to leave this thing running for a month or two to be absolutely sure no steel remains, but in the end this beaker sat in the back of my lab for nearly half a year. I mean, when this iron slowly rusted away, I finished my opal project, visited London, Kenya and Italy, and started like 10 other projects, so the moment I finally decided to resume this one, the iron beaker was well into chemical retirement. Its contents looked nothing like before, forming this black dry slab on the bottom, and the color change probably came from the steel's carbon, which stayed intact. There was also some salt crystallizing on the walls, and overall this thing looked quite rustic. Now, as the next step in making ferric ammonium citrate, I have to turn this solid iron mass into some water-soluble compound, and the one I plan to make is iron-free chloride. Making it from my rust should be pretty straightforward, and to start I have to rehydrate this iron slab, which I did using some distilled water. It quickly brought everything into a fine suspension, and before proceeding further I wanted to wash my rust to get rid of the salt and other soluble impurities. Instead of filtration, which would probably take forever, I added a whole bunch of distilled water into the suspension, and after stirring everything I left the beaker to sit undisturbed for a while. This made the insoluble rust particles fall to the bottom, while all the soluble junk stayed dissolved in solution, and I could now get rid of it by simply pouring it off. I repeated this process 2 more times, and now with my analytically pure rust slurry ready, I can turn it into iron-free chloride. All I have to do is heat it up with some hydrochloric acid, and I could do it in the beaker, but since I recently got a cool new condenser, I wanted to overcomplicate everything. For that, I transferred my rust slurry into a flask, then I got 100 ml of concentrated hydrochloric acid into the beaker to dissolve all the rust stuck to its walls. When they looked crystal clear, I got the resulting fuming apple juice into the flask and set it up for reflux. Reflux is just a fancy way of saying that I can now boil everything without losing any acid, greatly speeding up the reaction, and this very cool condenser makes it all possible. To start, I turned on strong heating to bring this mixture to a gentle boil. I also turned on some light magnetic stirring, and after a short while the reflux really got going with my gorgeous condenser working perfectly. Now, in terms of what's happening here, hydrochloric acid attacks the iron-free oxide along with all the other rust components, turning them into iron-free chloride, which colors the solution dark brown. With such strong heating, this reaction is quite fast, and after boiling everything for roughly an hour, I added another 100 ml of concentrated hydrochloric acid just to make sure all my rust reacts. This made the reaction mixture rise dangerously close to the condenser, but it fortunately didn't boil over. What's even more interesting, however, is that all the black carbon particles seemed to magically disappear. It was very hard to see in such a dark solution, but after a few hours of reflux it became nearly perfectly clear, and it made me wonder if the chemistry gods gave me a blessing and removed all the contaminants for me. To find this out for sure, when I felt that the reaction was complete, I disassembled the apparatus and filtered the still really hot contents of the flask through a cotton filter. It seemed that upon touching my filter, the carbon decided to magically reappear, nonetheless there was way less of it than I expected. Anyway, now with some crystal clear iron-free chloride solution ready, it's time to turn it into ferric ammonium citrate. For that, I first have to make it into iron-free hydroxide, and I could just use the solution as is, however, since I don't know exactly how much iron-free chloride I have, I first decided to isolate it. To accomplish this, I have to remove all the water, which sounds easy on paper, but in practice is always a pain. I mean, iron-free chloride is one of those compounds that have a deep, intimate relationship with water and want to be around it as much as possible, and drying it can only be done very gently since it can all just decompose when heated too strongly. Fortunately, I can boil off the bulk of the water without any problems, but removing the rest can only be done by air drying. This means that I have to pour all this iron liquor into a tray and leave it to slowly dry, which honestly doesn't sound too bad. One problem, however, is that iron-free chloride is really corrosive and is actually often used to etch many metals, to which my trusty tray is no exception. It didn't capture well on camera, but upon contact with the iron solution, the tray instantly lost its protective black coating, and upon seeing that, I panicked a little and quickly poured everything into a glass tray I stole from the kitchen. It shouldn't react with the solution, nonetheless this whole drying step started to really annoy me. To try getting over it as fast as I could, I bought the tray outside and placed it on the roof of my mom's car, which, being black, should gently warm it up under the sun. After a whole day of such treatment, it seemed like the water stopped evaporating, and upon bringing the tray back to the lab, I was quite disappointed. It turned out that iron-free chloride loves water way more than I thought, and even though there were some small crystals present, the majority of my product still was this goopy mess. I could waste even more time trying to crystallize it, but considering the absurd amount of time I already spent on this project, I was kinda running out of patience. Now, I didn't want to give up on finding out how much iron-free chloride I have, and after some thinking, I figured out a way to do it which doesn't involve waiting for centuries. Instead, it involves a tiny bit of math, and to start, I got my corrosive molasses into a beaker. I will now turn this solution into iron-free hydroxide by reacting it with some sodium hydroxide, also known as lye, and I will calculate how much iron I have by measuring the amount of sodium hydroxide required for a complete reaction. This sounds so simple, it made me feel like a genius, and to prepare a sodium hydroxide solution of known concentration, I weighed out 20 grams of it in a beaker and then poured in enough distilled water to reach the 200 ml mark. This should make a roughly 10% solution, and to react it with my iron-free chloride, I got the beaker with it onto a hot plate with steering and started slowly adding the sodium hydroxide solution. At first, it didn't really seem like much was happening, but at the chemical level, sodium hydroxide kicked out the chlorine from the iron-free chloride, itself becoming sodium chloride and resulting in some brown, insoluble iron-free hydroxide forming. It turned out that there was so much iron-free chloride present, I had to whip up more of the sodium hydroxide solution to react with it all, and I kept adding it until the mixture lost its yellow hue and a bunch of insoluble precipitate formed. Everything ended up looking like some fine mud, which was exactly what I was hoping for, and now my iron is only a couple of steps away from becoming ferric ammonium citrate. Also, I could finally run the calculations on how much iron-free chloride I had, and based on the roughly 50 grams of sodium hydroxide needed to react with it all, I figured that I made around 67 grams of iron-free chloride from rust. This is honestly a real nice yield, and to proceed with the synthesis I have to clean my iron mud a little, since there is a bunch of soluble contaminants in it that would later screw up my cyanotyping. The normal way of doing that would be filtration, but all my years of doing chemistry taught me that if something looks this muddy, filtering it equals intense pain. Because of that, I had to find another way to get rid of all the soluble junk, and the best thing I came up with was reenacting how I dealt with the rust at the beginning. This method also seemed just genius considering its simplicity, and to carry it out I got this heavy-duty beaker and poured all my iron-free hydroxide sludge into it. I now had to use a whole bunch of water to allow it to quickly settle to the bottom, and the water also preferably had to be hot to extract more contaminants and speed everything up. For that, I whipped out another glorious piece of my new lab equipment, which is this cool transparent electric kettle I use only for distilled water. That way I can have some hot lab-grade water whenever I please, which is another level of chemical convenience, and watching this kettle run is beyond mesmerizing. When the whole 1.5 liters of distilled water in it started to boil, I poured it all into the big beaker and stirred everything up to thoroughly mix it with the hydroxide. I then let this whole thing sit undisturbed for around 20 minutes, during which all the iron-free hydroxide settled to the bottom, allowing me to drain the top dirty water layer off. I repeated this process 3 more times and was honestly quite amazed by how nicely it worked. In the end, I was left with around half a liter of purified homemade mud, which based on my calculations should contain 44 grams of iron-free hydroxide, assuming 100% yield from iron-free chloride. It's more than enough to make the ferric ammonium citrate, and there's actually just a single step left in its synthesis. To carry it out, however, I first have to make something called ammonium citrate, which, as you've probably guessed from its name, makes up a good part of my target ferric ammonium citrate. Making it is fortunately really straightforward, and the first ingredient I need is some good old citric acid. I bought quite a bit of it from a chemical supplier, but the household stuff should work just as well. Now, to turn it into ammonium citrate, I weighed out 51.6 grams and dissolved everything in around 100 milliliters of distilled water with light heating and stirring. To make the ammonium citrate, I have to turn these 3 hydrogen atoms in my citric acid into 3 ammonium ions, and this is best done using a concentrated solution of ammonia. Now, pure ammonia is a very stinky and toxic gas, which is why it is almost always sold as a 25% solution in water, which, while being similarly nasty, is much easier to handle. I have to add a precise amount of it to my citric acid solution in order to get all the ammonium ions in place, and it's quite important to not overdo it since excess ammonia could easily screw up the synthesis later. To figure out exactly how much ammonia to add, I will use these handy dandy paper strips which turn red in the presence of an acid and blue in the presence of a base like ammonia. I will know that I added enough ammonia when the paper turns light green, indicating that the solution is neither acidic nor basic. Since I know that I have to add quite a bit of ammonia, for the first addition I just aggressively poured it straight from the bottle, which made everything weirdly milky for a while and changed the color of the paper to yellow. This meant that I now had to be really careful not to add too much ammonia, and by using a syringe and testing the solution a bunch of times, I finally achieved a beautiful light green color of the paper. This meant that my solution now contains pretty much only ammonium citrate, and I can finally proceed to making ferric ammonium citrate. For that, I came back to my iron-free hydroxide beaker, and after putting it on a hot plate and turning on strong stirring, I poured in the whole ammonium citrate solution at once. This, apart from releasing quite a bit of heat, didn't really do anything, and to form my target compound, I had to bring this solution to a boil. After cranking up my hot plate's heating, the solution started boiling really quickly, and I now had to hold it like this for around 20 minutes. In terms of what's going on here, the iron-free hydroxide and ammonium citrate slowly react, forming ferric ammonium citrate. Now, nobody really knows how this reaction proceeds since ferric ammonium citrate is actually not a real compound. You see, while most chemicals have a well-defined formula, ferric ammonium citrate is more of an idea than an actual chemical, since its composition heavily depends on the ratio of starting materials used to make it. Nonetheless, we know that every sample of ferric ammonium citrate contains ammonia, citric acid, and iron-free in some proportions, which heavily dictate the properties of the final compound. The ferric ammonium citrate I make should be dark green and be perfectly suited for making cyanotypes, which is all I really want. However, if there is enough interest, I could make some other varieties in the future and see how they compare. Anyway, after boiling this sour mud for around 20 minutes, I added 5.4 ml of fresh ammonia to keep the solution more basic. I also marked the current level of liquid in the beaker and now had to keep boiling everything for an hour. I also had to keep the volume of the solution constant by occasionally adding some distilled water. When the hour was up, everything looked pretty much the same as before, and to finish the formation of my ferric ammonium citrate, I added an additional 51.6 grams of citric acid and again boiled this thing for an hour while maintaining its volume. This time the solution gradually got greener and less cloudy, which was really good, and when the hour was up, I got it off the hot plate and passed everything through a vacuum filter. This should remove most insoluble contaminants. However, to make sure that there is no more free iron trihydroxide suspended in the solution, I passed it through a tightly packed cotton filter. It did its job very well, leaving me with a crystal clear ferric ammonium citrate solution from which I now had to recover my product. Much like the iron trichloride before, ferric ammonium citrate really loves water, and I wasn't really looking forward to drying it, but since I really had no other option, I tried to give it my best. First, I boiled the solution down and used some aluminum foil and a watch glass to make everything go faster. When it was at about half the original volume, I poured it into my trusty glass tray. I then used my kitchen oven to gently heat this thing overnight, which should really speed up the drying, and when I came back the next day, the solution looked quite funky. You see, a ferric ammonium citrate solution doesn't dry like a normal, well-behaved chemical would, forming this hard solid layer on top which prevents the rest of the water from evaporating. What's more, the whole thing progressively gets syrupier as it dries, making scraping off the top layer even more painful. It's really quite interesting how I experience more than one horrible drying step in a single project. Anyway, even though the ferric ammonium citrate didn't want to cooperate, I kept drying it, at one point switching the heat source from the kitchen oven to the top of my lab one. After a few hours of struggling, I managed to remove pretty much all the moisture from my product, which left me with those weirdly hard dark green lamps of homemade ferric ammonium citrate. It honestly looked really cool, and I was happy that after all the struggle I managed to make it from rust. Now, to store it, I first got the majority of it into a petri dish and then scraped off what adhered to the tray using this metal scraper. I then combined both portions together, and to make working with my product easier, I wanted to grind it all up. For that, I went and got my new shiny grinder, which is a ginormous upgrade over the old one. I then filled it up with the ferric ammonium citrate lamps and proceeded to beat the hell out of them. The grinder crushed them like they were nothing, and when I was satisfied with how powdery they got, I got everything onto a scale. I managed to make 134 grams of what looked like some green sugar, which is honestly really good, and in terms of the percent yield, I can't really calculate it since I don't know the exact composition of my product. Anyway, this much ferric ammonium citrate will be enough for hundreds of cyanotypes, and after getting it all into a jar, amateur chemistry style, I was now ready to do some art. Now, as I said at the beginning, making a cyanotype first involves preparing a light-sensitive solution. For that, I just have to dissolve some potassium ferricyanide and my homemade ferric ammonium citrate in distilled water, and for my first cyanotype, I went with the classic 20:14 ratio by weighing out 2 grams of the citrate and 1.4 grams of the ferricyanide. I then dissolved them separately in 10 ml of distilled water and then combined the resulting solutions to obtain this lime green cyanotype juice. Now, in theory, this solution as well as the dry ferric ammonium citrate are quite photosensitive and quote-unquote spoil under light. However, this is really only a problem under UV or sunlight, and short-term exposure to artificial lighting doesn't really affect them from my experience. Anyway, as the substrate for my cyanotype, I chose some plain old printer paper, and I specifically bought the thicker variety because it doesn't warp or fall apart as much as the regular stuff. To coat it with the iron solution, I used a kitchen sponge, which looks quite primitive and really lives up to the name of this channel. Nonetheless, it worked more than fine, coating the paper evenly and virtually streak-free. Anyway, with this extra fancy wet paper ready, I am getting really close to making my first cyanotype. To proceed, I first let the paper dry in the dark for a few hours, and when it looked like all the water was gone, I now had to take care of another very important aspect of creating a cyanotype, which is the UV light source. There are generally only 2 things strong enough to work, the first one being a UV lamp, and the second the good old sun. For my first cyanotype, I figured that I would go with the classic sun-based method, both because it feels even more DIY, and when I recorded this, it was really sunny outside. Now, I can't just throw my cyanotype paper onto the ground and expect any good results, and to enhance the quality of the print, I have to sandwich it between something transparent. After looking around, by some unimaginable stroke of luck, I found 2 gigantic glass panes just lying there, and they will be just perfect. I got them onto the floor of my patio, and with pretty much everything ready, I now had to find something to make a cyanotype of. Since it is my first one, I wanted to go with something classic and settled on various leaves I gathered around the house. To cyanotype them, I carefully got the photosensitive sheet of paper outside under my shirt to block out the sun, then with some surgical precision and light speed, I got it onto the glass pane, threw the leaves onto it, and sandwiched everything between the second pane. With this tight operation complete, I now had to wait a few minutes during which the cyanotype will be created. The first indication of something happening was the slow but quite noticeable color change of the paper from light green to blue. Now, there is quite a bit of funky chemistry going on in this small piece of paper, all of which is due to the chemical instability of ferric ammonium citrate. You see, being this bulky chemical mess, its components are bound together very loosely, and it doesn't take much for the whole thing to fall apart. This can happen in many ways, but UV light turns out to be ferric ammonium citrate's worst enemy. Upon being exposed to it, it gets all excited and then falls apart, producing a bunch of random chemical junk. It's not all random junk however, since we know that all the iron 3 gets yoinked into being iron 2. It basically changes flavor when looking at the sun, and this iron 2 formation is actually what makes cyanotyping work. You see, the rate at which it's produced directly equals the amount of UV light hitting the exposed paper, and where no light hits it at all, no iron 2 is created. This is why the paper below the leaves will remain white, and controlling the exposure time of a cyanotype is a very useful tool in determining how intense and detailed the final cyanotype will be. Now, for this cyanotype, I decided that 8 minutes in full sun should be enough, and when the time was up, I quickly retrieved my exposed paper and brought it back to the lab. I was kind of surprised by how cool it looked already, with the outlines of the leaves clearly visible and a blue color already forming. To make this cyanotype permanent, I have to wash away any intact ferric ammonium citrate so that it doesn't continue to degrade. I also have to actually form the Prussian blue dye that will give the print its final color. All of this is easily done by soaking the cyanotype in water, which gets rid of all the unreacted ferric ammonium citrate and gives the potassium ferricyanide a chance to shine. Until now, it was just sitting in the paper doing nothing. However, in the presence of water, it's able to dissolve and immediately react with the formed iron 2 to make Prussian blue. This reaction only occurs with iron 2, so no pigment will form in areas with no UV exposure, and it will also make the color permanent since the water-insoluble Prussian blue is formed inside the paper. What's even better is that this dye is very resistant to degradation, and if kept away from any bases, it can last pretty much forever. One important thing about a cyanotype's color, however, is that once developed, it gradually darkens over a few days due to some oxidation reactions happening between the Prussian blue and oxygen from the air. To reveal the true color of a cyanotype instantly, I have to force all the pigment to oxidize at once, and this is best done using fresh water and some dilute hydrogen peroxide. As you can see, it has a CGI-like effect when applied to a fresh cyanotype, making its color much more defined. It isn't all sunshine and rainbows, however, because if you bathe your cyanotype in the peroxide for too long or don't thoroughly wash it away afterwards, this happens. At some point, it basically turns on you, and instead of intensifying the color, it starts bleaching it. Fortunately, it didn't bleach my piece of art completely, and it still looked quite cool. To finish it, I threw 2 very good and heavy books onto it to undo any warping caused by the drying, and the next day my first cyanotype was done. Even though it isn't perfect, I am really proud of it, considering it was once literal rust, and with the overall process figured out, now it's time to make some improvements. First of all, I wanted to better control the UV exposure, since the sun, while free, can be quite unreliable. For that, I whipped out my trusty Chinese UV lamp, which will allow me to reject the sun and make all my future cyanotypes uniform and less daytime dependent. Since this lamp is not quite large enough to expose full A4 sheets of paper and my fume hood is not wide enough to fit those enormous glass panes, I had to modify my setup a little further. For the glass, I looked around some more and found this outdoor flame thing next to the big glass panes, and apart from some white rocks, it contained these 4 beautiful pieces of glass just begging me to take them. And take them I did. I mean, it seemed that my UV lamp was just made for this, and now the only thing left to improve is the photosensitive paper. I prepared a bunch more of these sponge-coated sheets using the solution from before. I also properly dried them this time using my oven. To make them fit the small glass pane, I went and got this old photo cutter, and after measuring out the exact width of the pane, I proceeded to cut all the paper with great satisfaction. This left me with a bunch of perfectly sized cyanotype paper sheets, and to finally try out all my new equipment, I assembled what I call the Cyanotyper 6000. It should make the results of every future run very consistent, and to test it out, I again gathered some random leaves, placed them on the cyanotype paper along with the glass pane, weighed everything down with some fine canned vegetables, and used a bunch of aluminum foil to make the light of the lamp more focused. I then turned this thing on with the exposure time set for 10 minutes, and when it was up, it was time to see the results. Compared to before, the exposed print looked quite a bit more detailed, which was very promising. Anyway, to develop it, I set up these 3 water baths in the back of my lab. The first 2 serve to thoroughly wash the print, while the third is for the hydrogen peroxide. This time I made sure to leave the cyanotype in it for no more than a minute and thoroughly washed it afterwards. I then dried it on low heat using my oven, and the results were honestly quite amazing. I mean, it definitely lost some detail and wasn't as vivid as I would like, but it was definitely better than the first one and proved that this new method has a lot of potential. Before using it to develop my grandpa's films, however, I wanted to experiment a little more, and the first thing I wanted to do was compare it with some commercial cyanotypes. You see, I bought this cyanotype set just for this purpose. It's composed of 2 bottles containing the same ingredients I use, and I was wondering if it will do any better. To test how this store-bought stuff performs, I filled both bottles up with water and combined the resulting solutions in a 1:1 ratio, forming this very dark mixture. Similarly to before, I covered a few sheets of paper with it, and after drying and cutting them, I now had something to compare my rust-derived stuff with. Now, apart from comparing different compositions of the photosensitive solution, I also wanted to move from cyanotyping leaves to some actual images, and to experience what cyanotyping the film will be like, I ordered some plastic printer sheets. They, along with my inkjet printer, will allow me to create some very crude, transparent negatives of pictures I can then cyanotype with. To test this funky paper out, I got my channel logo and using this handy dandy online photo editor turned it into a negative. I then printed it and the results were pretty decent, but definitely not as great as they would be on a regular piece of paper. Anyway, to test out this new process, I did everything the same as before and instead of some leaves, used the plastic negative. I did a single run with my homemade and commercial cyanotype paper, with the exposure time still being 10 minutes, and when it came to developing the photos, the results were pretty interesting. You see, the commercial cyanotype looked really underexposed, but the moment it touched water, it became very dark and eventually developed a nearly perfect shade of blue. After the peroxide washing, it became a little too dark, suggesting that I will have to cut down on the exposure time in the future. Overall, the store-bought cyanotype kit behaved as expected, delivering really nice results. Now, when it comes to my stuff, the results were kind of trash. I mean, it looked laughably bad next to an actually decent cyanotype, and I was beginning to doubt the quality of my ferric ammonium citrate. I didn't want to give up, however, considering how much time and effort I already spent on this project, and after some thinking, I figured out why mine and store-bought cyanotypes differ so much. It's not really due to the ingredient quality or the peroxide washing, but rather to the ratio of the ingredients, since this whole time I was using the original 1420 mix of potassium ferricyanide and ferric ammonium citrate. The commercial cyanotype kit, however, seems to use a very weird and strangely precise ratio, so being the good chemist that I am, I just ripped it off using some basic math, in the end coming up with my improved cyanotype recipe. It uses exactly 18 ml of distilled water along with 2 grams of ferric ammonium citrate and 0.8 grams of potassium ferricyanide. To see how it performs, I coated a few sheets of paper with it, dried and cut them for hopefully the last time, and for the first exposure using my new paper, I used this new negative I made with a photo of a blackbird taken by my brother. After exposing and developing it, I was left with quite a decent cyanotype, and while it still wasn't as good as it could be, I was more than happy I managed to achieve something like this myself. Now, since I finally figured out a good cyanotype procedure, I played around with it a bit, printing more negatives and developing fine cyanotypes of things like this nice hypnotic pattern, Among Us, the B-movie script and Kenyan sunrise. I also cyanotyped a picture of my cat, which took 3 takes to master, and this was her reaction to it. Anyway, after gaining some first-hand cyanotyping experience, I figured it's finally time to develop my grandpa's photos. For that, I again looked at the films, and when I chose a few photos that I liked, I cut them out and sandwiched them between my new cyanotype paper and the glass pane. After exposing them for 12 minutes, I did another run, this time with the wider films, and when I started developing them, the results were just insane. After washing and drying, I was left with 2 incredibly high quality cyanotypes, and the level of detail on them far exceeded everything I had made before. This was especially visible on the wider film, where the high quality negative gave rise to some very beautiful images. It's so cool to think that my great-grandfather once took these images and stashed the negatives to presumably never be seen again, while I not only discovered them, but using the power of amateur chemistry and some rust, turned them into these beautiful pieces of art. To be honest, this is exactly the kind of thing I aim to do on this channel, and this whole project is just another example of the absolute awesomeness of chemistry. Now, I think that this whole cyanotype journey was one of the coolest things I've ever done, and what started as a tiny side project evolved into a hefty video, which is kind of becoming the norm nowadays. Anyway, this beautiful project wouldn't ever be possible without you, my amazing viewers, and I have to sincerely thank you all for watching. If you'd like to support what I do, please consider subscribing, liking the video and sharing it with a friend. If you want to directly contribute to improving my videos, as well as having access to a lot of exclusive content like my lab tour, I invite you to become a patron. Speaking of my patrons, they motivate me to keep making content and allow me to have the funds necessary to keep taking on unique projects, and I want to dearly thank each and every one of them for their generous support. Anyway, for now, thanks again for watching and see you all in the next video.